Hello, today we are going to go through the optimization of bicycle crank arm. I am Tsang.
I'm Olga.
I'm Bikas.
A bicycle crank arm is an important part of a bicycle which connects the pedal and the chainring, allowing a bicycle to move forward. However, the load from the pedaling can affect the stress and deformation of the bicycle crank. We are going to analyze the deformation and stress of the bicycle crank using FEA by answers. And we're going to optimize the crank design, focusing on reduce the mass without increasing the deformation. And below are some design parameters can affect the mass. For example, the hole size of both ends, the length of the crank, and the thickness of the crank. Next page. So we start with the geometry of the crank arm. And for the answers, of course, we're using the static structure for doing this. And here are some basic dimensions of crank, just like the figures we see in the previous page. The length of the crank is about 210 millimeter. The body thickness is 44 millimeters. For the circular hole, the diameter is 15 millimeters. And finally, for the square hole, the side length for each is 12.25 millimeter. Next page. Yes. After that, we extrude and make our FEA model of the crank arm. And here's the isometric view. And we chamfer for most of the edges of the crank arm. And we have to mention that the material we are using is aluminum alloy, which the density is 2,770 kilo per cube millimeter, and the Young's modulus is 71 GPa.
Okay, so for our mesh, we used a mesh element size of 1 millimeter for the entire geometry. The smaller mesh elements were created at areas where higher stress was calculated, and to improve the mesh, we added chamfers to smooth out the edges and reduce the stress in the region. And for this geometry, the smaller mesh was needed in the square hole as we found the inner edges to have the highest amount of stress, and the mesh element size used here was 0.25 millimeters. Next slide. For our analysis result quality, we made assumptions and created boundary conditions to help generate a realistic analysis. We applied a 900 Newton external load or a remote force analysis in the negative y direction, which can be assumed from a bicycle pedal. We also applied a fixed support at the square hole to constrain movement for analysis. Next slide. For deformation analysis, we obtained a maximum deformation of about 0.4 millimeters and average of about 0.1 millimeters. In this case, the deformation is expected to occur when the applied external load set 4 centimeters away from the geometry results in a rotational motion due to the bicycle pedal. So we can expect a slight deformation at that end of the geometry. Next slide. For the von Mises equivalent stress, we analyzed this by solving for averaged and unaveraged cases, and it was found that the average maximum stress is about 357 megapascals, and minimum is about 0.18 megapascals. The unaveraged maximum was 448 megapascals, and minimum was 0.12 megapascals. And these different results proved that the analysis did not converge. Although this is a challenge, it should not have a significant impact on the effectiveness of our analysis because theoretically the results do not converge at sharp edge geometries, regardless of how the mesh sizing is done or the smoothness of the edge. But instead, the results increase the stress magnitude of the infinite to an infinite amount. And to tackle this issue, we use chamfers to smooth out the edges of the square hole, which is the location of the max stress. And this was the best solution to reduce the stress and obtain the best results. Next slide. For radial stress, we also analyzed this by solving for average and unaveraged cases, and it was found that the average maximum stress is about 182 megapascals, and minimum is about negative 162 megapascals. The unaveraged maximum was 285 megapascals, and minimum was negative 205 megapascals. And once again, the results didn't converge for the same reason mentioned in the previous slide, and the same solution was effective in solving this as well. Next slide.
So to run the optimization for this part, we started with the original design of the thickness for 44 millimeters and the hole diameter to be 15 millimeters. At these points, the geometry mass was 0.38343 kilograms, and the total deformation maximum was 0.38678 millimeters. We decided to run 10 design points to run the analysis, and we decided the hole diameter range to be between 16 to 21 millimeters, since it needs to increase for the optimization to be reducing mass. And we used a range for the crank thickness to be between 38 to 43 millimeters, since the crank thickness needs to be reduced for the mass to decrease. And below, on the graph below, you can see the 10 data points that we used for the analysis. In this graph, we can see the design sensitivity results for total deformation. And in the top graph, we can see the total deformation versus thickness graph. And we can see the relationship that when the thickness increases, the total deformation decreases. And below, we can see that the graph that shows that when the hole diameter increases, the total deformation increases as well. For these graphs, we see the relationship between both parameters and its mass. In the top graph, we can see that when the thickness increases, the geometry mass increases as well in a linear relationship. And in the graph below, we can see that when the hole diameter is increased, the mass decreases. These graphs are the 3D graphs that show the relationship between both parameters and the results. In the top graph, we can see the relationship between the parameters for thickness and the hole diameter in relationship with the total deformation maximum. And in the graph below, we can see the relationship between mass, thickness, and the hole diameter. For the design optimization setup, we decided to add two optimization parameters. The first one being over here in row number 3, we can see that the parameter for geometry mass, the objective was to minimize it. And in row number 4, we can see that the parameter for total deformation maximum, we decided that the values should be lower or equal than the upper bound, and the upper bound was selected to be the current total deformation maximum. Below, in the table below, we can see the candidate points for this run after showing the 3 points for optimization. And those points, we decide to verify the design points. And after that, in this graph, we can see how they were imported to the table of design points. These are the lower 3 points. And we chose point number 15 to be our current design because it met our specifications for reducing mass and without giving up total deformation. In this final result, we were able to reduce mass by 10.76 grams, and we only gave up 0.0061 millimeters of total deformation. After running the design points from the generated from optimization. We set point number 15 to be our current design. And to prove that our design was changed into the geometry, we go back into the geometry model and we check how the design parameters were updated based on our optimization run. On the top left, you can see the width was set back to 42.649. Below, you can see how the hole diameter was increased to 16.047 millimeters. And the mass in the middle table, we can see how the mass was reduced to 0.37267 kilograms, and the total deformation on the right side was only changed by 0.006 millimeters. And we proved that our optimization results were correct, and we were successful in running the optimization of mass design. So thank you so much for listening to our presentation.
Thank you.
Thank you.
Thank you.